Today we're going to talk about nth roots and rational exponents. The definition of a rational exponent is this: the nth root of a is equal to a to the 1 over n. Rewrite each rational exponent as a radical raised to an exponent, then evaluate if possible. For 6 to the 5 halves, using the power of a power property for exponents, I can rewrite 5 halves as 1/2 times 5. So I can rewrite this as 6 to the 1/2 all to the power of 5. 6 to the 1/2 would be square root of 6. We don't need to write that little 2 outside. A radical without this little number is automatically a square root. We don't know the square root of 6 and we can't simplify it, so here's our answer. Similarly, I can write 12 to the 3/4 as 12 to the 1/4 to the power of 3. 12 to the 1/4 is 4th root of 12, and this is to the power of 3. Could 4th root of 12 be simplified? That would only be if a perfect fourth is a factor of 12. 1 to the power of 4 is 1, but 1 goes into everything, so that doesn't help us break it down. 2 to the power of 4 is 16, which is bigger than 12. So this is as simple as it gets. 8 to the 2/3 can be rewritten as 8 to the 1/3 all squared, and 8 to the 1/3 can be rewritten as cube root of 8. We can actually simplify this because 8 is a perfect cube. The cube root of 8 is 2, which is still being squared, and 2 squared is 4. Go ahead and try part D. And now, is 81 a perfect fourth? Yes, 3 to the power of 4 is 81, and 3 cubed is 27. Real nth roots of a. Let n be an integer, n is greater than 1, and let a be a real number. If n is an even integer, if your root is even, then if the number under the root is negative, you'll have no real nth roots. If the number under the root is 0, you'll have one real nth root, because the nth root of 0 is 0. And if the number under the root is greater than 0, you'll have two real nth roots, plus and minus, the positive and negative versions. If n is an odd integer, so if your root is odd, you can take the odd root of a negative number. That would give you one real nth root. 0 is still one real nth root, and if the number underneath were greater than 0, you'd still have one real nth root. To find the indicated real nth roots of a, let's rewrite as a root. If n equals 3, then we're looking at the cubed root of a, which is negative 216. Can you take the cube root of a negative number? For example, negative 2 cubed is negative 8. This will have one real nth root. The cube root of negative 216, it's going to be negative 6. For part B, your root is 4 and your radicand is 81. We have an even root and a positive radicand. That means our answer should be two real roots, positive 3 or negative 3, because the 4th root of 81 is 3. We did this in the beginning where we were able to rewrite a rational exponent as a product of powers, such as 16 to the 1/2 cubed. 16 to the 1/2 is square root of 16. The square root of 16 is 4. Now let's cube it. 4 times 4 times 4 is 64. Now you may be wondering why positive and negative 4 were not answers for root 16. This is because we are simply evaluating an expression, not solving an equation. And then you may say, well, we weren't solving an equation in number 2, but they asked for the indicated real nth roots. The real nth roots of a is based on solving an equation, not simplifying an expression. So 32 to the negative 3 over 5. But where does the negative go? We can't have a negative in an nth root. A negative has to go to the exponent. 32 to the 1/5 is asking for the 5th root of 32. The 5th root of 32 is 2. Now we have 2 to the negative 3. And remember that a negative exponent means the base of that exponent is on the wrong side of the fraction bar. If your power is negative in the numerator, then you need to move that base to the denominator to make the power positive, and vice versa. So 2 to the power of negative 3 is definitely not negative 8. It's 1 over 2 to the power of 3. This negative symbol only tells me I'm in the wrong location. Now 2 cubed is 8, so 1 over 2 cubed is 1 over 8. Find the real solutions of the following. Use a calculator to find the decimal approximations of all irrational solutions. Now we have some equations with exponents that are greater than 2. First, you have to isolate the term that is to the power of 5. So let's divide both sides by 4. Because x is to the power of 5, we need a property of equality that is inverse to the power of 5. Remember, our goal is not to have x to the 5, but to have x to the 1. For x to have a power of 1, this power of 5 would need to multiply by 1 over 5. That means both sides of this equation are put to the power of 1 over 5. The left side becomes x to the 1, and the right side becomes the fifth root of 32. The fifth root of 32 is 2. Remember, if your root is odd, you'll only have one real solution. We could have also written this solving with no rational exponents and just roots. The inverse operation of power of 5 is root of 5, so we'll fifth root both sides. That makes x equal to the fifth root of 32, which is 2. You can show your work with a rational exponent or a radical, whichever you prefer. For part B, make sure the term or quantity to the power is isolated on that side of the equation. It is because the entire group is to the power of 4. So for this quantity to only have a power of 1, we need to raise both sides of the equation to the power of 1/4 or fourth root both sides. Once you use the nth root property of equality, you are simply left with the radicand on the left side. Now, I don't know the fourth root of 21, and 16, the smallest perfect fourth, that isn't 1, doesn't go into 21, so I can't simplify the fourth root of 21. My last step would be to add 3 on both sides. But wait a minute, how many roots do I have? My root is even, and my radicand is positive, which means I should have 2 real nth roots, meaning I forgot to put a positive or negative because I have an even root. We would not put positive or negative on an odd root. Now add 3 to both sides and you get your answers. X equals 3 plus or minus fourth root of 21. Now the directions also asked us to use a calculator to find the decimal approximations of all irrational solutions. To type these into the calculator, you can use a root or you can use a rational exponent. If you used the rational exponent 1 over 4 and your calculator is not in math script, be sure you put parentheses around this whole fraction, otherwise your calculator will interpret it as 21 to the power of 1 divided by 4. Notice how I still have equal signs because I have written the ... showing the exact number, not a rounded version. But let's go ahead and round each of those solutions to 3 decimal places. And now that they've been rounded, let's write x is approximately equal to. If the answer is asked us to round it to 3 decimal places, then we don't need the approximation symbol because we would be giving x in the terms that the directions asked for. Because these directions were not very specific, I decided we should round to 3 decimal places, which is the expectation for AP Calculus. A hospital purchases an ultrasound machine for $50,000. The hospital expects the useful life of the machine to be 10 years, at which time its value will have depreciated to $8,000. The hospital uses the declining balances method for depreciation, so the annual depreciation rate in decimal form is given by the formula R equals 1 minus s over c to the power of 1 over n. In the formula, n is the useful life of the item in years, s is the salvage value in dollars, and c is the original cost in dollars. What annual depreciation rate did the hospital use? We have an equation for rate. Do we have s, c, and n? When you plug this into the calculator, you get the decimal 0.167446 and so on. So approximately 0.167, and our depreciation rate was in decimal form, so as a percentage, 16.7% is the annual depreciation rate the hospital used.